Hello folks, welcome back. Today's TEmS talks, our threat emulation system series of talks, is going to center on an RF stimulator, but this time it's not to stimulate an electronic warfare system. It actually is an electronic warfare system component, and it's designed for the stimulation of radar systems so that they can work on their electronic protection against electronic attack. So what we'll be showing you today is a PC that houses an RF system on a chip card. That digital card has 8 A to Ds and 8 D to As on it, and it has an inherent architecture that lends itself perfectly to digital RF memory or DRFM applications, which we'll describe in great detail today. This particular product we're going to highlight today is one of our 2 entries into our Article product line. Article stands for Adaptive Real-Time Closed-Loop Emulators, and one of the 2 products is for the stimulation of radar systems, and this is what we'll show you today is the real-time closed-loop electronic warfare system, and it is a DRFM jammer. So to introduce you to the functionality of the real-time closed-loop electronic warfare system, which is the DRFM jammer component in our Article Adaptive Real-Time Closed-Loop Emulator product line, what we want to show you is the RF SoC card, the 8 A to Ds and 8 D to As built into that, how we're using it to actually do the demonstration today. And what we're doing is, just so happens that the 4th of the 8 outputs of the DAC, the digital analog converter card, is actually generating a signal based on software we have. The software is controlling the RF SoC card, controlling one DAC, and we just have a preset setting for a pulse train and a pulse waveform that we're going to use to input to the DRFM. So what we have is DAC 4 is first feeding the A to D input for channel 1. So our pulse train is going into one of our analog to digital converters, and that's going to be feeding the digital to RF memory. It's going to be capturing it, it's going to be storing it, it's going to be playing it back, and we'll show you that feature in a second. It's also teed off and going into channel 1 of our high-speed digital oscilloscope. What we have on channel 2 is the output of DAC 1. So it digitizes the input, stores it, and plays it back. We have one channel feeding the digital oscilloscope for the demonstration, and then the other channel is, the other teed off output is also feeding a spectrum analyzer, so we can show it to you not just in the time domain on the scope, but also in the frequency domain on the spectrum analyzer. So the host computer for the real-time closed-loop electronic warfare system, RT-CLEWS DRFM jammer, is actually a Linux box running our RF SoC card. We also have Windows versions of this exact same card as well, running on Windows instead of just Linux. And the GUI we want to show you here is just a piece of software we've used for the demonstration to control the parameters that we're going to be showing you some of the features of the DRFM jammer. So again, past the section of code that's actually generating the input signal that the electronic warfare system is going to be seeing and modulating after it stores it and plays it back, the other portion of the GUI, which is the most important portion of the DRFM jammer, is the target mode, which includes disabled, so it won't be playing back anything that it captures, a fixed target playing it back, and both inbound and outbound targets. Now the only mode we're going to show you in our series of videos today is a very simple multiple range false target application, and a subset of that is also the minimum delay cover pulse, which is also expanded into a possible application for a range pull-off jammer and also a Doppler pull-off jammer. So an RGPO or a VGPO we can do with the same setup. So the signal we're going to be putting in for the DRFM jammer to capture is actually centered at 250 megahertz. We could run it at a much higher frequency, but to show it on the scope, it just makes it easier to do. Right now we're only putting out one pulse in a 25 microsecond pulse in a 1000 microsecond or 1 millisecond pulse repetition interval. And the interval for the dwell, if you will, is 1 millisecond, and we're just using that to show the update rate on some of the instrumentation. It could be a much more complicated waveform than that, but that's just for the demonstration today. And then what we're going to be doing is we're going to be changing the output of the DRFM target mode for both fixed repeats and also inbound and outbound repeats, because we're going to be doing moving target returns from the one signal it does get in. And then for the false targets in this particular setup, we can change the number of returns, the amplitude relative to the input, which is very important, especially when you're doing cover pulse type things, the head-to-head interval between the rising edge of the pulse on the first return and all the other subsequent returns, the delay from when it sees energy to when it puts out energy. We have a minimum delay mode, which is normally used for cover pulse, and we can move that out beyond just the input side. The delay, and also we have a Doppler we can add on top of, modulation on top of that to simulate apparent range rate. Also induces Doppler, and we can simulate that as well, and we'll show you all those features one at a time. So the very first setting we're going to show you is a fixed output, a single return after it sees energy, and how it sees energy is actually selected by how we decide to trigger the DRFM to sample and store the input pulse. For right now, what we're selecting is any certain threshold on A to D activity beyond what typically is noise is going to be assumed to be an incoming pulse. And we would also take an external trigger, say from like a video detect log amplifier or some other feature like that. So for right now, we're going to actually sample on the RF energy seen by the A to D. We're going to put out just one return at a fixed range. So it's either ground to ground or air to air, but traveling at the same speed. And relative amplitude is no gain, no loss. And for right now, head to head doesn't matter because we're only putting out one pulse. But we're going to put out a fixed delay of 20 microseconds after the energy is actually sampled at the beginning of the pulse. And we'll show you that if we go to the digital oscilloscope. On the digital oscilloscope, this is our input pulse to the DRFM, and the output pulse to the DRFM on 20 microseconds per division. One division would be 20 microseconds. So you could see that we're putting out a pulse at 20 microseconds from when it first sees the energy. Okay, so for the first DRFM mode we're going to show you is multiple range false targets, with and without Doppler. And the first thing we want to show you is the control for the delay from when the energy is sampled to when the energy is retransmitted. So for right now, we have a start of 20 microseconds, and we're going to shift that to the absolute minimum delay of just 4 nanoseconds. So that's the minimum delay mode, and you would normally start there if you were doing some kind of range gate pull-off technique where you need a cover pulse close to the actual skin target return before you start walking it away in range. So what we're going to do now is we're going to put the first return with a fixed range offset out to 10 microseconds, and what we're going to do then is just make multiple returns instead of just the one. So there's your 10 microsecond return. Remember, it's a 25 microsecond input pulse with a single fixed range offset, 25 microsecond output pulse, but we're going to up the count to, say, 5 false targets. And if you stay there, we're also going to change the apparent range between the multiple range false targets. And that control will do, say, 40 microseconds from the 25 microsecond pulses. And we'll double the number of multiple range false targets to 10. And we can go back to, say, just 4. Okay. Now let me show you another feature. Come on back here. What we're going to do now is we're not going to leave it as a fixed offset. We're going to actually make it move either inbound toward the target or outbound away from the victim radar. So we're going to start first by changing the initial delay to much greater than 10 microseconds, and what we'll do is we'll walk it in. So I'll move this out to, say, 50 microseconds for the initial. Actually, let's make that a lot higher. Let's go to 150 for the initial offset. And now what I'm going to do, I have a fake velocity in the system, and I'm going to make it move inbound toward the target. Just for the demonstration purposes, that's essentially a Mach 3 velocity moving in at 1,000 meters per second, but it's good for the demo so you could actually see it. We can crank that up even just a little bit more, so it moves just a little bit faster. And we could also change it from a target moving inbound to the victim radar to a target moving outbound, and I'll do that now. It's going to move away, apparently, in range. So we're starting where we left off with a large 200 microsecond delay and 4 fixed targets. So now we're going to go back to just 1 target return. Let's go back to showing you the 4. If you look at the signal on the spectrum analyzer, that's a very complex sin X over X mix of 4 targets in a certain PRI. But it's a lot easier to see if we just go back to 1. That's your typical sin X over X curve for a fixed pulse width in PRI. And we're going to talk to that in a minute when we change the Doppler on the target return. Okay. And we're going to go back to a high velocity inbound motion, and we're going to look at our spectrum analyzer because right now we don't have a Doppler enabled. So let's put a marker of what a 0 Doppler offset looks like. And come to the control. We're going to enable Doppler with a very high velocity just so that you can see on the spectrum analyzer what a Doppler offset looks like. So right now we're going to not only enable the Doppler but use the velocity that's simulated in the range motion, and as we go to the spectrum analyzer you should see it shift. So we're going to shift it even more. Now if you look at where it's shifted, it's a higher frequency because we have an inbound target. An inbound target moving into the victim radar is going to look like a higher frequency because of the positive Doppler shift of the targets moving closer together relatively. We're going to change right now to an outbound trajectory with the same Doppler offset. So it should move just as far to the right as it did, just as far to the left as it did to the right. And then back to no Doppler. Back to Doppler enabled, and we're going to have the Doppler offset from where it is. And then again, back to a positive Doppler shift inbound target from none. Okay. Okay, so the next and last feature we're going to show in this short series of the DRFM Jammer today is the ability to not only place the multiple false range targets where we want them in both time and Doppler, but also the ability to change the amplitude of the relative returns as seen by the victim radar. So for right now, we have a control for, we have a transfer function between the input to the A to D and the output to the D to A. And what we're calling 0 right now is we can go up higher in amplitude and also lower in amplitude. So what I want to show you here, we're going to go back to 10 multiple range false targets, and the starting relative amplitude, we're first going to go up in amplitude and then we're going to go down in amplitude. So for right now we're going to go up to 3 dB higher, and that's what 3 dB higher looks like in the voltage world. And we're going to go to 6 dB higher than the normal zeroed output, and here's a full 12 dB higher than the normal output. And we could also go negative, so negative 3 dB and negative 6 dB, depending on what we really want to do when we're trying to fool the victim radar. Okay, so we've shown time control, number of multiple range false targets control, moving in and out in range, also coupling that with the velocity simulated to create a Doppler shift, so to make the range gate and velocity gate pull-offs realistic. And that's essentially it for today. So with our Giga-tronics article, adaptive real-time closed-loop emulators, our DRFM entry into that, which is the real-time closed-loop EW system, the RT-CLEWS, we have the perfect complement for a jammer component that allows you to test the electronic protections of your radar system. Okay, folks, so just to make some of your questions or concerns clear, we're not offering up to anyone all over the world this capability. The hardware and software and firmware is definitely ITAR restricted, and while all of our hardware, firmware, and techniques are very white world and generic, nothing here is actually classified. It's not tied to any one particular program with any one particular set of parameters. It's just a generic starting point. The whole idea here with ITAR restrictions and classification concerns is we're generating and providing an open architecture framework of both hardware and software so that our customers have a foundation, a base on which that they can build. Now they can do it in two ways. They can take our product offering with the start, the rudimentary foundation of our code for the real-time closed-loop electronic warfare simulator and its DRFM jammer component, and they can build on top of that with their own expertise and resources and their own secret sauce for their techniques, or their customers' need for emulating a threat that they need to test against. The other way to work this is if our customers don't have the expertise themselves, or they just don't have the resources to throw at the development, we'll be more than happy. Giga-tronics does have a secret facility and clearances, and we can get a DD254 from you folks, be right onto the program. You can give us your classified parameters, and we could actually work that into the functionality of the firmware and the hardware to your specific parameters for the threats that you really need to have us create for you so that you can test against us. And again, one last word of both advice and caution. We are professionals. Don't try this at home. Thanks for coming today.